So if I have a force acting on an object, so I have some object here with some force acting on it, and the object undergoes some displacement. So basically I want to multiply them together. Now I know from Newton's second law, the force, if that is the net force, let's go ahead and make this the net force, the total force, that would be equal to mass of the object times the acceleration of the object dot delta x. We've seen this before. One of the cake formulas, I know that Vf squared equals Vi squared plus 2a dot delta x. Therefore, a dot delta x is equal to Vf squared minus Vi squared over 2. Notice that I'm multiplying, doing a dot product between two vectors here, so I should end up with a scalar, and these are all scalars here. So this becomes mass times Vf squared minus Vi squared over 2. Dividing by 2 is the same as multiplying by half, so I have 1/2 mass times Vf squared minus Vi squared. I'm going to go ahead and distribute, so I have 1/2 mass Vf squared minus 1/2 mass Vi squared. And that's all equal to this. Well, this seems to be a rather generalized formula here, and if you use calculus, you'd end up in the exact same place. This right here, which, because it shows up twice, I'm going to just use a letter here. I'm going to use a capital K to represent this 1/2 mv squared. So I have K final minus K initial is equal to that. And I'm going to use a special letter for that one. I'm just going to use W. Now, since this is the net force, this should be the net value here. And so we have this relationship here. This is a final minus initial. So this is the change in K is equal to W net. And so this actually is known as the work energy theorem. W stands for work. And K doesn't stand for energy itself. It stands for a particular branch of it that stands for the kinetic energy. And so kinetic energy is basically, it's this energy which describes the motion of an object because it's related to the speed. Take it one step further. If we are talking about, in that last derivation, we talked about the net force. Well, there's actually two types of forces. There's the conservative force, and then there's non-conservative forces. All forces are either one or the other. What in 151 and 251, gravitational forces are conservative, ideal spring, or elastic force are conservative, and pretty much and everything else is non-conservative. So my net force dot delta x, in other words, my net work, is equal to the conservative force times delta x plus the non-conservative force dot delta x. This would be the conservative work plus the non-conservative work. Non-conservative work, it's called non-conservative because energy is not conserved, and so this is equal to the change in energy. And so I have delta K is equal to work conservative plus delta E. If I subtract delta K from both sides, and actually let's subtract delta E from both sides, so I have delta K minus delta E is equal to the conservative work. Energy, we basically have two types in classical physics. There's potential and kinetic, so I have delta K minus delta K plus delta U. U is the symbol for potential energy. And delta K is going to cancel out. The minus sign will distribute, and so I end up with negative delta U is equal to work conservative. And so we have these three relationships here. We have the total work or net work is equal to the change in kinetic energy. We have the non-conservative work is equal to the change in energy. And we have the conservative work is equal to the negative change in potential energy. So this is the total energy. Since down here when I said energy we had kinetic and potential, this is more specifically known as mechanical energy. But this energy right here, the kinetic energy is the energy related to how fast an object's going. This potential energy is energy related to its position, about how much effort does it take to put an object into a particular location. There is another type of energy known as rest energy. And most of you know the equation, although if I just said, hey, write it down, you might not know it. But if I just said E equals, a lot of people do know what comes after that, mc squared. I'm going to make one change though. This is, put a little subscript 0 here next to the mass. This is known as the rest mass. And the rest mass is something that you actually have been dealing with in any lab where you put a mass on a balance and the balance is sitting right there and you're sitting right there. In other words, the object's at rest relative to the balance, relative to you, then you're finding the rest mass. And the reason why I differentiate that is that when you get into relativistic effects, this rest mass is not necessarily the one in play. If I take an object and zip it up near the speed of light, and there's a collision, then the relativistic mass becomes more important and not the rest mass. That is something for the end of physics 152 or 252, or if you take it at another school, potentially it's in the what's generally considered the modern physics or semi-modern physics section of the physics courses. So that would be the rest mass. Basically, and for trivia at this point, we don't do much with it in 151 or 251, so you don't need to worry about that. But basically, the work-energy relationship's right there, and more specifically, the work-energy theorem, the non-calculus derivation.